Last time we talked about the thermal conductivity. We got into transferring energy in three different ways. Collisional is what we're talking about with thermal conductivity. There's also convection, like the convective ovens and air fryers that we have, and then radiative transfer of energy. Thinking about our liquid nitrogen Dewars and even the thermoses and the YETI cups that we have now, now you can understand the design of those particular insulating vessels, right? So what do they have associated with them? So what makes a YETI so good? Yeah, but how is it insulating? So again, the insulation is opposite of thermal transport. So if you can stop thermal transport, collisional transport of energy, you have a good insulator.
Didn't we say it was adiabatic?
Yeah, adiabatic. And this is collisional transfer of energy is a way to ruin adiabatic systems, right? So it's conducting thermal energy, and so if you can stop that, you have an adiabatic barrier, no heat transfer. Okay.
The metal walls, they act kind of as like a heat sink.
Yeah, they do. Metal does conduct heat pretty well, but they make it as thin as possible. Okay, so the thin wall is part of it. The thin steel wall is a part of their ability. So it heats up pretty quickly. There's not a lot of thermal mass. So it doesn't take a lot of joules out of your drink. So let's say we're storing something hot. Okay, we put the hot in there. The steel that's touching the hot liquid heats up nearly instantly. Okay, but it only takes about 0.6 joules to raise a gram of metal 1 degree, whereas it takes 4 joules to raise a gram of water 1 degree. Okay, so it takes, what is that, 642 back, 1/7 of the energy to raise the steel 1 degree. So it takes up 1/7 of the energy water would take up, like if you had a water insulated device. So water is terrible insulation. Okay, so the steel comes up to heat, but then if the steel is connected with our humid air in Huntsville, that's not going to be very good because that humid air is going to take away the heat. So do you know that the YETIs have double walls? They have 2 walls. Okay, so they have a metal on the inside and a metal on the outside. It's not just so that you don't feel the heat on the outside. I mean, if you've ever had one of those steel, ceramic, or enamel-coated steel coffee mugs, like for camping. They pour boiling water in there, and you touch that thing. Guess what? That's 212 degrees, and you're going to burn the crap out of your hand. Okay, so the YETI has the double walls, but what's in between the walls is the key to stopping collisional transfer of energy. So what's between the walls in a YETI?
Hot air.
Is it vacuum insulated?
It's vacuum. You take away the molecules, you don't have collisions. You don't have collisions, you don't have convective transfer. Okay, or you don't have collisional transfer of energy. So it's got to be a vacuum, and that's the only thing that's really made them so good, is that for their cups, they have a really low pressure in there. It's not a perfect vacuum, but it's very low. And so they've somehow come up with a technology to produce those cups in mass production and get a really good vacuum on the inside. So it's just a Dewar flask. There's nothing new about that. We've known about Dewar flasks for a long time. Used to make them out of glass. So your Stanley thermos, my dad's Stanley thermos, when he would take to work with his coffee in it, was a double-walled glass insert and had a vacuum pulled in. Now, the one thing that it also had was a silver coating. So they would put, silver nitrate solution in there and an aldehyde, and it would precipitate out the silver, reduce the silver, and make a silver mirror on the inside of that glass. Now, what was that about? That has nothing to do with collisional transfer of energy.
The radiative part?
Yeah, so if we get rid of the collisional, we can still have radiative transfer of energy. So the inside of that flask would be hot, and it's giving out infrared. And if that goes out through the glass, then we're losing heat that way. So they put a silver mirror on the inside to reflect the infrared back in.
That makes sense. Big, old thermos. Yeah,
and you look inside and it's all silvery. It's that reflective coating on, and it's not on the inside of the glass. It's on the, so here's the inside with your liquid. Then you've got a glass wall. Then you have the silver coating inside the vacuum part. and then there's the outer wall and so on. So this is ways to stop. And of course, if you don't have gas, you don't have convection either, because convection is currents of gas. So this we went through again this ideal thermal flux, looking at the ideal gas, and we came up with this constant for ideal gas like argon of 0.005 watts per degree per meter. And then we compared it to let's compare it to things in our home. So energy migrates in response to a thermal gradient. If you have a thermal gradient, the higher the gradient, the higher the flux, right? So you've got this, slope of the energy as a function of distance. And so the gradient is the slope. So if you have a huge temperature difference, that's the gradient going up to high temperature. The flux is going the other direction. So the steeper that gradient, the steeper the slope, the faster the heat transfer. Okay. And so this is very important in your home because we like to keep our interior of our home comfortable no matter what's going on outside. And so if it's really cold in the winter, we have a hot area inside our home. We've got a thermal gradient at the windows, the walls, and at the roof, and so on. And so in order to maintain our comfortable environment inside the house, we do a lot of management of heat. And so this is just some information in terms of our consumption. All of the heat generating devices, so fridge is generating heat in the room, but also cooling the inside. It uses 14% of our energy consumption. The AC and heater between 16 and 10%. These are all dependent upon the thermal gradient outside. So in the winter time, our heat goes way above 10%, especially with a heat pump. They're not the greatest in terms of maintaining heat. The water heater and clothes dryer, freezer, and then the fan that's pushing the air through your central system if you have that, and then the stove and the oven. Look, all of these are related to heat in some way, or cooling, pumping heat from one spot to another. Okay, and that's 67% of your bill, essentially, at the best case, right? In the winter, deep winter here in Huntsville, when it gets so cold, right, we're running our heat pump. It runs constantly. It just can't keep the thermal gradient with the outside, and so it's just really spinning the meter. I always joke that we could cut wood with our meter, because it's spinning so fast. And so, and people talk about, switch your light bulbs to curly bulbs. You know what I'm talking about? The little fluorescents, compact fluorescents. And LEDs are even better, but maybe that's 10%, 9% of your bill. So, even if you never turned a light on the whole month, you might save 10% of your bill. Yeah.
We sure do feel good buying them.
We feel really good buying them. Yeah, we really do. We'll talk in the next set of the material in the course about energy conversions and energy sinks and sources. And so I'll have some data to show you what would be better for certain homes and so on. But for now, it is good. Again, it's good to save 10%. That's a huge amount. If you average that over all the households in the country and in the world, I mean, that's an enormous amount of energy. So I'm not saying that's bad, but I'm saying it's not realistic to think you're going to cut your bill in half, yeah. And so heat, and generally, is 30% up here if you add up just those 30% of consumption. Another way to also save money and be more efficient is to get rid of all of these heat sinks, places where heat leaves your house and where cold comes into the house. So drafty windows, even your fixtures and so on. So the way we stop this with air leaking out of the house is that we seal it up and we put in insulation. So notice these insulating layers are everywhere there's the gradient. So whether it's winter and you've got a thermal gradient going into your house, and so then the flux would be going out, you put that insulation wherever there's a gradient, and then you seal your doors. And so in the 70s, when we had that sort of energy crisis panic, everybody sealed up their homes, okay, and sealed up their windows, and we put all kinds of weather stripping in and everything like that. There's just a big push. PSAs on the television all the time. And so we sealed up our homes, and guess what we saw? Yes, we saw good, more efficient homes, but we also saw an increase in lung cancer. And especially certain parts of the country, because we had radon sneaking up through the concrete in our basements and through the rocks in certain areas. Texas doesn't have a lot of uranium deposits down below in the bedrock, but in like parts of New Mexico, in the Midwest, Pennsylvania, they have a lot of uranium down in the rock, and uranium decays and produces radon gas. And radon gas is in equilibrium with its surroundings. Guess what happens? You've got uranium oxide in a rock. It's chemically bound, and it moves along. We'll do this in the next set of the notes. And when it becomes an ideal gas or a noble gas, all of a sudden it's not an oxide anymore. Or it's not covalently bonded to anything. And so it's free. So it percolates up and moves and migrates through the rock, and concrete is rock too, so it fills the concrete and eventually starts to migrate out into the people's basements. And normally, if a drafty house, it wouldn't be a problem. There was enough exchange with the outside air that radon exposure was fairly low. I mean, it would have been worse in the basement regardless, but still, you've got a drafty window here in the basement, you would have exchange with the outside air. But you seal that window up, and now the radon concentration builds up in the basement. You go down there to change the laundry out. A lot of people have their laundry in the basement, and they go in there and they're breathing in radon. And then it gets in your lungs, and then it just bad luck, right? It decays in your lungs, and now it's no longer radon, it's radium. And radium is a group 2, and radium's going to go wherever calcium goes. And calcium gets stuck in your body in the bones, and it sits there, or it gets in your lungs and generates alpha particles and so on. And so we saw some lung cancers start to develop. So they think that about 14% of lung cancers are due to radon gas. Yeah. So they put radon detectors in the basements, and our cousins lived up in Pennsylvania for a while, and they said something about radon, and I was like, really? What's this? And they said, oh yeah, we have a radon detector in our basement. I was like, really? You got to show me. Well, it was just a PVC pipe. It said radon, do not touch. You know, it was a little detector, and they had somebody come by and pull the little detector and read how much was in there. Yeah, so it was more like a film badge than anything else. It was just tell you how much your exposure was in the past.
I remember in the 80s then, because I remember when I was a kid in the 80s, and I started hearing news reports about radon gas.
Yeah.
And that makes sense if in the 70s to save energy they started doing that in the 80s.
Yeah, so you seal them up, and then all of a sudden we discovered, unintended consequences. Yeah. Which, I mean, it's fine. It's not like we then said, oh, no, let's go back to drafty houses. Let's detect the radon and let's mitigate it. Let's have a fan in the basement that does at least exchange the basement air. And it's a price that you pay, but then the rest of your house isn't drafty, but you could exchange the air for your basement. Yeah. And so then when we get to thermal insulation, we talked about the YETI cup. The vacuum is best. The next is heavy trapped gases. And then the aerogel is right below that. So this is a sort of a promo picture of this aerogel. It's an expanded, sort of like a foamy silicon oxide matrix. So it's a solid, but it's have you ever picked up pumice, like a lava rock pumice? It's a solid foam, like it's a foamy lava that's cooled. It's mostly ash, but there's a lot of air pockets in there, and it's like styrofoam, only it's not styrene, it's rock. Okay, it's a really light foamy rock. This is a similar thing. It's a solid, like rock-like structure, but the lattice is huge, so there's lots of air pockets in there.
Back in the day, it used to be very popular for yards.
Pumice, yeah.
Everybody, back when I was a kid, everybody had it.
And that big red lava rock too. Yeah, exactly. And so this is a funny little promo picture. They've got on a ring stand. They've got this aerogel, which you can kind of barely see the edges of it, and they've got a blowtorch underneath and the matches on top. And so that's pretty insulating. Now, eventually that heat may make it through, but I mean, the point is, if you were to just flash this propane onto the matches, they'd light instantly. And here you have these matches sitting on top of that insulator. So that's an example of the aerogel. And they use that kind of concept for the space shuttle tiles. When they re-enter, the frictional forces as they're slowing down this object coming in from space, create enormous temperatures. And this was able to insulate the space shuttle. The Columbia burned up on impact because it was missing a couple of these tiles on the front edge of the wing. So when it took off, a piece of insulation came off of the cryogenic hydrogen oxygen tank and struck the front edge of the wing and damaged one of the tiles. And that was enough to destroy the whole space shuttle on reentry. Yeah. So as they were reentering, the heat burned a hole through the front part of the stabilizing wing, and then it just started, destroying it from the inside of that wing. Then they started losing control, and then it started tumbling, and then it was done. Yeah. So then you have still gas is insulating. Light trapped gases, meaning like helium and so on, are not as good as heavy trapped gases like argon or krypton. Okay, but still gas is better than liquids or foams. So then you can have foams like styrofoam, a fibrous material like spun fibers, or cotton or something like that. So fibers, because they don't compress. And again, it's a function of density. So vacuum is the least dense thing. Remember, density is mass per volume. And so if there's no mass in a given volume, that's the best. It's the least dense, so that's the best insulating. And then non-dense solids and then liquids are way down here. Liquids are non-insulating. And then dense solids would be the worst. And so here's, again, that kind of idea with the different substances, different liquids, different gases. Here's glass, 1.2. Whereas like carbon, this is, again, thermal conductivity. So the green are for conducting substances. And I talked about carbon coating of tooling last time. Yeah. Okay, so let's go back and do this top hat. Okay. All right, so let's start. Having troubles?
I was just in it this morning. Yeah, but now.
What's it looking like? What's it doing?
Well, it's because our 14-day trial ended. But I checked this morning to go into the app that let me in, so I didn't.
Oh, that's weird.
But
What'd you say?
I just got struck by that.
Yeah. You're struggling over there. I'll give you 15 more seconds. Yeah. All right. 5, 4, 3, 2, 1. Okay, so definitely water's more dense than air. What does that have to do with cooling?
Maybe it holds a cooler temperature longer than air would.
It's so think about thermal conductivity. So that's the concept. And so we said the insulation was the opposite of density. And so water is less insulating than air. So it sucks the heat away. Yeah, it's conducting heat. Just like water, just like wires conduct electricity, water conducts heat. So you can think of it that way. So the circuit in an automobile for cooling, the engine is generating an enormous amount of heat, and we want to conduct that heat away. So we have a circuit of water, So the water goes by the engine, pulls up that heat, takes it to the front, the radiator, which again, the way we get rid of heat with air is surface area. So we run the water through these microscopic tubes, well, maybe not microscopic, but milliscopic tubes that have lots of fins. And so it doesn't take much to raise metal by a certain amount. But if we have all these fins raised to the temperature of that water and then air blows by those fins, we have a lot of surface area. And so the air can pull that heat away from the metal. So we have a dense area of heat where the pistons are. And then we have a really dispersed area of heat where the radiator is. And so we have this huge surface area for air to take away that heat. And so whenever you're trying to use air to take away heat, you need surface area. And that's the heat exchanger. So it's just exchanging the heat from the water with the air. So that room or ambient temperature air is going by this 200-degree water, and those little fins are at 200 degrees, and that air will take away the heat and drop that temperature. So it's just a circuit. It just conducts the heat from the engine out to the radiator, and air takes it away. And so it's fantastic. You could use something better than water. Let's see if there's any other. Let's see. Here's water. Thermal conductivity. Liquid water at around its boiling point is 0.6. Are there any other liquids that would do better than that? Mercury. So we could have mercury cooling for our engines. What a mess that would be. It's a toxic metal, right? But it would do great. Yeah, it would be fantastic, yes. So.
We would use any aluminum engine parts, though.
Yeah, maybe not. That's right. Metal compatibility. Yeah, that's a great point.
And with damage, any kind of damage and leaking.
Oh, yeah. What a horrendous mess, yes. So that's when you like scientific solutions. Yay. Toxicology. Boo. So. Let's see. Is this one still on? I don't know why I didn't show the top hat on the video, but that's fine. Now, there's a thing in your household, like when you're buying insulation for your house, they talk about the R value, and it's R for like resistance to heat flow, and this is the flux in watts across the temperature gradient, and it's the primary value for rating different commercially available insulation properties. And so here is how it's related to the thermal conductivity. So here's the thermal conductivity down here in the denominator. So if it's got a large thermal conductivity, it's got a low resistance to heat flow. That makes sense, right? It's conducting heat. If it's got a small thermal conductivity, then it has a high insulating value, a high resistance to heat flow. Okay. And then there's an area here. That area would be, just think of a window. So like you can buy different windows that are double pane windows, and they fill them with a gas in between. It'd be hard to get a vacuum because the pressure from the atmosphere would be pushing on that window, and in the middle of that window would be an enormous amount of pressure. And even if the glass didn't break, it'd probably bow in until the glass touched. And so you'd have glass-to-glass contact, which is going to be conducting heat. So it'd be really hard to get. I mean, you could do it with really thick glass, but then your expense is really going up there. But to get a vacuum in between would be the best. They can't really do that. So they got to put a gas in there. What kind of gas do you want to put in your double pane windows? So just, yeah, look at the periodic table. Like which gas would you use? What would you put in there? And then if you know anything about our composition of our atmosphere.
Argon.
That's right, argon. Argon's about 1% of our atmosphere. So we have a lot of argon. It's fairly cheap. Yeah, we can separate argon from nitrogen and oxygen, and then we can put that argon gas in our double pane windows. Eventually they leak though, and they'll let water and vapor in there, and then we have a higher conductivity, a lower R value. But look at the units here. We've got per square area. So we have a square area of our window. We have the thermal conductivity of argon. And then we have a thickness of that gap, that M. So the resistance value goes up if you have a thicker gap of gas. That's the M, the top part, the distance. If you have argon versus helium, helium would be terrible. It's a really fast gas, and it's related to velocity, right? The mass is in the denominator, square root of mass in the denominator. So argon is going to move slower than helium. So helium, small mass in the denominator for velocity, and so it's going to be transmitting heat from one side to the other because it's colliding so fast. It hits the hot side, picks up more energy, delivers it to the cold side, and gets rid of some energy. So let's go into diffusion. So here's our gradient. Here we have, again, a matter gradient. We might have other kinds of molecules over here and a few over here. So it would be species dependent. And so this is not diffusion. I'm trying to draw these other molecules just so you show that there's a concentration gradient related to a particular species. And so it's going to flow over here until it's all at the same concentration everywhere in the box. And so this is related to the mean free path and the average velocity. So this is going to be our transport coefficient for diffusion. Remember the mean free path, there's two different types. There's a gas diffusing into itself or a gas diffusing into another gas. And so this would be the mean free path of like gas 1 diffusing into gas 1 plus gas 2. Okay, so using the earlier numbers for argon, we have the average velocity and the mean free path for argon. And so that would be our diffusion, sort of our ideal gas diffusion coefficient. So much, really small. So it's 10 to the minus 5 meters squared per second. And so that's, you can kind of see that it's sort of like particles per meter square area. So they're passing through this square area of a meter every second. So even though the velocity is incredibly fast, 397 meters per second, gases diffuse pretty slowly, especially in 1 atmosphere pressure. And so this is why, because they go a little distance and they hit a particle. And then they go another distance and they hit another particle. So they're changing direction all the time because they're hitting particles. So these are all the collisions. And you see after all those collisions, it's only gone this distance. So that's what slows diffusion down. It's this random banging around in the thing. So think about it like a dance floor. Okay, trying to cross a dance floor. It's not easy, is it? Okay, and sometimes even though you want to go straight over there, you kind of go around people, and so you bounce around. Okay, and sometimes you get knocked down. Right? I like to picture it. I love weddings where they have the little kids running around in between the adults and the dance floor. So that's gas 1 diffusing into gas 2. So I see all of these things so much. It's like, look, we got Fickian diffusion here. So,
Professor, what were the little circles?
just other molecules that are hitting. So every time they change direction is a collision. Okay. Now this can happen not just in the gas phase. Now we're talking about gas phase because it's kind of ideal situations, but this can happen in a solid too. So that radon gas bouncing around, making its way through concrete is going to take a long time. Okay, but eventually it'll diffuse out. And so this gas is moving along. Now think about once it gets out of that concrete, then it goes a lot further, a lot faster because it's going into a different medium. Okay, it's got a longer mean free path. It goes further before it hits something. Okay, now this is this Stokes-Einstein equation for a large spherical particle in a fluid. So this would be the radius of the particle here. This would be the viscosity of the fluid. KT or RT, depending upon if you're doing joules or joules per mole, etc. Okay. Now, a particle diffusing through its own fluid, you just have a slightly different ratio here. So you've got a 4 instead of a 6. Okay. Now on the homework, there's a bunch of equations in this set of notes, but I'll show you which one that I'm thinking of wanting you to use in some of those problems, and it's this next one. So this time dependence, Fick's second law, is dealing with these equations. And so let's say we have a candle here in the room, and it's got my favorite smell, that creme brulee smell. I just love it. Okay, or vanilla, that's my favorite too. And so this would be the, after 333 seconds, this seems strange why they picked those numbers, but that's what they did. They've got here, it's pretty concentrated by the candle. Okay, and then sometime later, actually, this would be I light a candle, deliver a certain amount of smell, and then I blow it out. Okay, so this is a snapshot when I took the first picture, and then over time, the smell near the candle drops. Okay, and it diffuses further into the room. So it's the same amount of smell, and it's just diffusing out as we go. Okay, and so this is what this curve is showing, and that's this sort of mean, RMS, this root mean squared distance. So we have this RMS value here. Since we're talking about 3 dimensions, I'm going to do the RMS values here. And this is how they change over time right here. So the square root of 6, the diffusion coefficient times time. So it's a square root dependence on time. Okay. So this is in 3 dimensions, and it kind of matches. We got a factor of 6 here. In just 1 dimension, we have a factor of 2. So linear dimensions, if you have some kind of contaminant that leaks into a pipe, so you did a repair or something and you got something nasty in the pipe, and it's going to diffuse in both directions. But that's like a linear system because it's all in 1 dimension. And so that would be this XRMS. The X would be the distance it travels in a pipe over time. And it would be that diffusion coefficient of that substance in another fluid. So like a big particle in another fluid would be the diffusion coefficient. Now, if you're given, of course, if you're given this and you're given time, you could solve for D. If you're given D and time, you could solve for X, etc. So it's really 3 factors, the square root dependence. So these are the equations I'm wanting you to use on the notes. There's diffusion coefficients all throughout, and every year when we get to this homework, people are like, I don't know which one to use, or I'm using this one and it doesn't make sense, but this is the only one that has time in it. Okay, so that's obviously a giveaway. And now you just need to determine, are you talking about a 1-dimensional system or a 3-dimensional system? And then here's some examples of actual, experimental diffusion coefficients. And so we can see hydrogen, really the lightest gas here, this 1.604, argon 0.1. Okay, so you can see really a drop, the power of 10 in terms of argon. And again, this is diffusion. So this is related to the speed of the gas and moving around, that average velocity. But also this, makes sense in terms of our understanding of the kinetic theory of gases. Now here's gases diffusing through other gases. And so here's hydrogen diffusing through helium. And so it's not much different, okay, than it was up here. Let's see. Here's water diffusing through air. So there's our humidity. Okay, so that's if it's in humid outside and the AC goes off in this building, the humidity of this building is going to rise. And this is going to be the diffusion coefficient of that water diffusing into this building because we're no longer condensing the water out in our AC. Okay, let's see what else. This one is important. I thought we had oxygen here, but we just have air. So air diffusing into water. Okay. Pretty small, 10 to the minus 5 centimeters per second. But That's important for our fish, right? Because they have to have oxygen, and then we need to get that oxygen diffuse down into water. Okay, so a lot of practical applications. All right, so let's jump in. We don't have a lot of time, but we can at least get started on the next one. Or I can show you, I'll jump right to that equation, Poiseuille's equation, that you'll need for the homework that's due Saturday. So let's do that.